Thank you, Heather. So this talk is a little bit of a heresy. It's trying to explore the idea that while functional programming has a tremendous amount to teach us all, that it might just be the case that mainstream wide-spectrum languages like Java or C# or Scala may have even more to offer us in terms of using functional techniques to confront real-world problems than pure functional languages do. And obviously, like, I have some self-interest in this thesis, right? Like, this is what I do. And despite the fact that a lot of people, I think, just wish Java would go ahead and die already, I'm actually quite optimistic about Java's future, and I'm passionate about moving Java forward because of the huge leverage that it has. We have 9 million developers, and if we can help just some of those 9 million developers learn to program even just a little bit better, then the effect there on how the world programs is really substantial. When I was invited to do this talk, at first I was a little bit surprised because, after all, Java is primarily an object-oriented language, and OO is a little bit out of favor these days, and one of the themes of Kurion is emerging languages, and Java is definitely not an emerging language. But as it was explained to me, Kurion is dedicated to the idea that we're kind of all searching for the answers together, and to some extent we're all kind of imposters here. So I like this idea, and I took this as license to talk about a few things that I don't know anything about. So the first topic I don't know anything about that I'm going to talk about is sports. All right, and in particular, we'll talk about sports rivalries, right? Every sports team has a rival team, the team their fans love to hate. And, such as, I'll use an American example, the rivalry between the New York Yankees and the Boston Red Sox. Fans love their teams, but a lot of sports fans are even more focused on hating the other team. And so, to make this concrete, let's imagine a typical Yankees fan and a typical Red Sox fan. And, let's think about these two guys. Let's think about them from, well, who am I? Let's think about this from an object-oriented modeling perspective, right? What are the behaviors that they share versus those that separate them? And they actually have a lot in common. So to start with, of course, they're both people, and they share the behaviors that people have. And they're both sports fans, so they share the behaviors that sports fans have, like doing the wave and painting their face and spouting statistical gibberish. And they both think that the other is the embodiment of all that is evil. But if you step a little bit away from these two guys, you realize they're the same guy, right? Really, I mean, even in the object model, they don't even get their own classes. They just get different constructor parameters, right? So this is a topic that, of course, has been explored throughout history. And for example, the original Star Trek, explored this in one of the episodes called "Let That Be Your Last Battlefield," which is that we focus so much on our differences that we miss our overwhelming commonality. So in this Star Trek episode, most of you have probably seen, because we're all geeks here, the crew encounters this species of humanoids that are half black, half white. But some of them are white on the left and some of them are white on the right. And of course, they hate each other. And all they want to do is kill each other. And, there's only two of them left. They're all dead except these last two guys, and they're still focused on killing each other. And of course, from the crew's perspective, they can't even tell the difference, right? You guys are both half white, half black. Why are you so upset? And of course, the social message here is about as subtle as a sledgehammer. But sadly, we play this story out in our community every day. I mean, so imagine what we look like to normal people when we're arguing over spaces versus tabs, or text editors. From the outside, from the outside perspective, the spaces guy and the tabs guy are the same guy. Right? And the observer is thinking, and they're upset at each other not even over code, but over this completely non-functional aspect of coding. And meanwhile, the observer is thinking, if these two idiots could just get over their stupid argument and learn to work together, then maybe my car would actually be able to talk to my phone. So this brings me to the next subject about which I know nothing: cultural anthropology. Now, you'll notice sports fans will say things like, "we won" or "we lost," even though they had absolutely nothing to do with the winning or the losing. And this has to do with, the creatures we are, the biological creatures we are. We're naturally wired to form into tribes. And tribes could be formed along a lot of dimensions: spatial, social, spiritual, experiential. But, this impulse to form tribes and to subordinate our identity to those tribes. It makes sense from an evolutionary perspective. It's a good defense against being eaten by tigers. But we don't live in an agrarian society with marauding tigers anymore. We live in a technological society, and we're pretty much insulated from the risk of being eaten by tigers, but our brains are still wired the same way they always have been. Now, there's nothing wrong with tribalism. Tribal membership encourages us to learn from each other, to help each other collaborate. These are all good things, but it has a dark side too, and where it can get dark is when we start to demonize members of the other tribe rather than asking, what can we learn from them? And I have to say, it's not such a great thing that as programmers, we're really bad about this. I mean, really bad. We define our identities as Python programmers or C# programmers or functional programmers, and then we engage in these pointless debates about why the other is wrong or foolish for preferring such primitive tools or tabs. The reality is, as programmers, we all have so much to learn about building correct, robust, maintainable, secure, easy to use, cost-effective software that we should be ashamed. And certainly we shouldn't be criticizing others about tabs or VI or static types or objects or actors, because the user doesn't care whether the code was written in Haskell or Object COBOL. They just want their phone to talk to their car, and that's actually kind of reasonable. So the tribal division I want to focus on today is functional programming versus object-oriented programming. So these days, functional programming is popular, and so not surprisingly, it's gotten really popular to criticize object-oriented programming. And it's easy to find articles or blogs or conference talks about how and why OO has failed to live up to its promises, which, okay, to be fair, is totally true, but let's be realistic here. Has there ever been a programming technology that has lived up to its hype? So when I was preparing this talk, I watched about a dozen of these videos, and they all played the same tune. They took examples of object-oriented programming done badly, misapplied, and then proceeded to bootstrap from, well, it didn't work here, to it doesn't work at all. And again, to be fair, there are plenty of examples of OOP done badly. So these guys had plenty of material to work with, but just because something can be done badly doesn't mean there's nothing to learn from it. So, while some of those rants, have a point, and a lot of them do, I think they're going about it the wrong way because there's an awful lot of, if my tribe is right, the other tribe must be wrong here. But OO doesn't have to be wrong in order for FP to be right. It's a false dichotomy, and we're spending all of this energy on the anti, on the against, when we could be learning from each other, and we certainly have a lot to learn from each other. So this brings me to kind of the main theme of my talk today, which is rather than identifying ourselves as Python programmers or C++ programmers or functional programmers, we should be focused on being better programmers, because we all have so much to learn. We should seek to learn as much as we can from as many paradigms as we can. So to become better programmers, my advice is we all need to learn classical FP. We all need to learn classical OO. And then we need to strive to rise above them both. Okay, that sounds cute. What do I mean by that? Well, languages and paradigms are tools. They're just tools, and no one tool is ideal for all situations. The French writer Émile Chartier once said, "Nothing is more dangerous than an idea when it's the only idea you have." If we become too married to one idea or one programming paradigm, we're going to try to apply it even when it's not applicable. We're going to try to distort the problem so that it fits into our idea. A programmer that's skilled in multiple paradigms is just much more likely to find the right solution to a given problem than one that's only skilled at one of them, regardless of what language they're programming in. And the right solution might not be pure OO, might not be pure FP, or pure anything. It's more likely a blend of multiple disciplines. And in fact, it almost has to be, right? Because neither OO nor FP are really complete disciplines, right? Pure FP has no notion of computational resources, such as memory or threads or file handles. And pure object orientation has no notion of a computation that isn't localized within some entity or component. But real programs running on real machines need to consider both. So, as I said, object orientation has a bit of a bad reputation these days, and some of it is deserved and some of it isn't. And certainly it suffered from having arrived on the scene under tremendously inflated claims and expectations. So I don't know how many of you were programming in 1985, but it was pretty nuts. And by 1990, the hype surrounding objects had reached ridiculous proportions. Most of the OO code out there is what I might call Sorcerer's Apprentice OO, where you take sensible principles and then you apply them to their ridiculous extreme. So, for example, encapsulation is a powerful tool. Let's encapsulate everything. Encapsulation is a powerful tool, but I don't need it at every boundary. I mean, I might want a heavy lock on the front door of my house, but I surely don't need one on the closet of my bedroom. Most OO orthodoxy treats family members and burglars with about the same degree of distrust. Which means that, like, I have to unlock the door every time I want to get my shoes out of the closet. And to make matters worse, as we sort of write our programs and we're sort of feeling our way around in the dark, the boundaries are often drawn before we even have a good, clear design for our program, leading to the equivalent of like a bank vault door not only on every closet and bathroom, but sometimes even in the middle of the hallway. So no wonder people think OO is cumbersome. But this isn't really what OO is about, although sadly it's what comes to mind for a lot of people. And we largely did this to ourselves, right? So I'll take my share of the blame, right? In the Java world, we have this Java Beans convention for components, which was originally designed for one thing, right? Dynamically discoverable visual components in an interactive editor, which was a great application for OO. And then along came the Learn Java in 21 Days crowd, and these books said, apply these conventions everywhere. Every class should look like this. And of course, we got the worst of both worlds. We had all the ceremonial overhead and friction, and none of the abstractive value. Good job. Okay. But, a lot of you have probably read, some of the articles, or I'm talking about, like, there's this rant called The Kingdom of Nouns, which is all about why, Java is stupid. And I think they think that they're railing against OO, but really what they're railing against is a cartoon exaggeration of OO. The conventions that were right for graphical component framework are probably downright silly for most domain objects, but that doesn't make the technique silly, right? So I totally understand the motivation for dumping on OO this way, and it's certainly, I'm sure it's therapeutic for some of us, but what worries me is that it just makes us worse programmers, because it closes us off to what we have to learn from other tribes. So, all right, if that's not what OO is, then what is it? Well, let's step back a little bit. Let's step back from C++ and Java and C#, which are object-oriented languages for sure, but they also carry a lot that's not intrinsic to classical OO. So Alan Kay, one of the fathers of object orientation, once said, well, I made up the term object-oriented, and I can tell you that I did not have C++ in mind. And if he were saying that today, he'd say the same for Java or C#. I'm not slagging off on C++ here. C++ and Java both emphasize inheritance, but class-based inheritance isn't essential to OO. It's just one way to get polymorphism. Similarly, static typing isn't essential to OO. Smalltalk was dynamically typed. The essence of OO is that computation proceeds by objects sending messages to each other. These messages don't have to be statically typed, they don't have to be synchronous, they don't even have to be local. You send an object a message and it does something. Maybe it performs a side effect or returns a value or sends a message to somebody else. And this gives us polymorphism because the target is free to respond in any way that makes sense for that message. And whether this polymorphism happens to come from classes or from prototypes or from nasty stateful logic is really just a matter of bookkeeping. But complex systems do need dynamic dispatch. They do need polymorphism, and typically OO languages give you a pretty easy way to express that and reason about it. Okay, what about state? In the OO world, state is owned by objects, and to access an object state, you send it a message. Which brings us to the other major contribution of classical OO, which is encapsulation. OO languages give developers a straightforward way of saying only this code can access this state. And if you think about where object orientation came from, go back to the procedural world we were in, before 1985. And one of the big problems and one of the big impediments to programs growing beyond a certain size was reasoning about program state. If all the code in your program can access a variable, then in order to reason about its possible values, you have to analyze the whole program. Encapsulation lets us take this global analysis and shrink it down into a local analysis, where I only have to look at 50 or 100 or 1,000 lines of code to conclude something useful. And that enables programs to scale larger. So, okay, that's classical OO. What do we mean by classical FP? If you ask, people, what's the essence of FP, the typical first answer is something like, well, immutability in pure functions. Or maybe they'll say, well, pure functions as first-class values, or function application by substitution. Now, in reality, very few functional languages actually behave this way all the time. And with good reason, right? Because dealing with things like state are nasty, and simulating state and I/O with monads is, while fascinating, is not actually how most people want to program. And, classical FP doesn't give us an easy way to reason about things like memory utilization, which is actually an important thing that we need to think about in our programs. So most functional languages make some practical concession towards the messy real world via some direct support for I/O and mutation, and they accept the strictness that entails, and then we rely on programmer discipline to not use these things when we shouldn't. So okay, let's take a nice oversimplified comparison between these two paradigms. In OO, computation proceeds by sending messages to objects. In FP, it proceeds by applying functions to values. If we up-level this to the scale of a program, we say an FP program, well, that's just a function. It just takes its input and transforms its input into an output. OO programs have a little bit higher impression of themselves. An OO program is really something more like an executable model of an entity. And for any given situation, one or both of these views might be useful to us. With respect to state, in FP, our programs sort of swim around in this sea of collectively owned data that's transparent. Anybody can inspect it. Things are more opaque. There are these little opaque islands of data that's owned by objects, and each object is king on its own island. And there are times when encapsulation is absolutely a lifesaver in terms of managing complexity, to say nothing of security. And there are times when it just plain gets in the way. And as professional programmers, we're going to encounter both of these situations, and we really ought to know how to tell them apart and how to deal with them, and hopefully rise above the distinction. So you'll often hear this comparison, oversimplified as, in OO, everything's an object, whereas in FP, everything's a function. Every programming style has an obligatory, everything is an X summary, which, everything is an object or a function or an actor or a peanut butter sandwich. These characterizations are useful for about the first 5 minutes of learning a new paradigm. But after those first 5 minutes, I think that everything is an X, simplification is actually pretty destructive, because in reality, not only isn't everything an object, nothing is an object. Right? Nothing is a function. And certainly not everything is a Java bean, right? So objects and functions and actors, they're just models, right? And these models are useful to help us understand our code, but we shouldn't confuse them for representing reality. So we can choose to model things with objects or actors or functions with varying degrees of fit and fidelity in the hopes that the messy complexity, of the program can be managed. But there's this huge leap from use X to model Y to everything is an X. And it's not a very healthy one. It's clear that everything is an object is wrong, but our objections about it are usually in the wrong place. Usually we're objecting to the object part when in fact we should be objecting to the everything part. This everything is idea was like so overplayed, even by the late 80s, that in the paper Future Trends in Database Systems, Michael Stonebreaker said, if I hear the phrase everything is an object one more time, I'm going to scream. But he was an objects guy, right? It wasn't the object part that he thought was bad, it was the purism. And I think that FP purism today is no more attractive than OO purism was 30 years ago. So yes, of course, we need to abstract things away from the real world in order to have any chance of solving them with software, because the world is so full of messy, accidental detail that we have to filter some things out. But we have to keep our eye on the goal, which is solving a problem in the real world, and not a problem in software. And to do that, we probably need objects and functions, and maybe actors, and maybe even peanut butter sandwiches. So, the problem with falling in love with our tools is that we risk mistaking them for reality. So, in the real world, we have a problem we want to solve, like I want to make a phone call from my car. And we decide, for whatever reason, wise or not, that the easiest way to solve that problem is to turn it into a software problem. So we transform our problem into a set of inputs seen by a program, and a set of desired outputs that correspond to our goal, and then we write a program that turns the inputs into the outputs, and we're done, right? Well, hopefully we're done. Now, you all recognize this diagram, right? So there's some process by which we transform a real-world problem into a set of abstract software requirements so that we can solve our problem in the more tractable domain of software. So let's call this mapping F. And I think the big mistake that we all make is that we take it as an article of faith that F is a homomorphism. And that it preserves all the interesting structural properties of the problem that we're trying to solve. So all we have to do is take our problem, transform it into the abstract software space, solve it over there, transform it back, problem solved. The more that there's a mismatch between our chosen everything as an X and the real problem that we're solving, the more likely we'll end up with something that ticks all the boxes on the marketing requirements sheet, but doesn't actually solve the problem. Now, as programmers, we're comfortable writing programs. We're a little bit less comfortable working in the real world. It's actually kind of easy to forget that we're working in a synthetic domain, and we confuse writing the program for solving the problem. This is something that we should watch out for. In our more arrogant moments, we might describe what we do as building abstractions for a living. But abstraction is a double-edged sword. If you look it up in the dictionary, we find lots of definitions, some of which are a little bit humbling. Abstract could mean reduced to an idealized form, to separate away all the confounding details to reveal the essence of something, and that's certainly the kind of abstraction that we all want to be associated with. But it also means difficult to understand. And I'm sure we've all seen the second meaning when we look at other people's code, right? But even, the first meaning is a little bit suspect. Different details matter at different times when you're trying to solve real problems. So by necessity, the abstractions we use in programming must be leaky. And this is a kind of depressing fact to have to admit. So we use abstraction because we hope it's going to help us manage complexity and support reuse. Whether it be behavioral abstraction or data abstraction or representational abstraction. But abstraction isn't an end unto itself. It's a tool for solving problems. And we need to be able to continually revisit whether our abstractions are really serving the user or whether they're merely serving us. Remember, the user doesn't care about our abstractions. They just want their car to talk to their phone. Okay, so I'm sure it comes as no surprise by now that I kind of like object-oriented programming. And I like functional programming, and I'm okay with that. And it took me a while to get there because, well, all the tribal noise. For a while I started to wonder if so many folks are moving on from object-oriented programming to functional programming, and I still like object-oriented programming, what might that say about me? Well, I hope it's not this. But I think the real explanation is that my experience of programming is different from that of many developers. Most of the code I write these days is platform libraries. And I was very gratified to see a number of examples of people using platform libraries that I'd written on the slides in the talks this morning. So, but if you're writing platform libraries, you're on the other side of a boundary from most of your users. And that changes the story. And in fact, you're like on the other side of a lot of boundaries. Maintenance boundaries, versioning boundaries, encapsulation boundaries, compilation boundaries, compatibility boundaries, security boundaries. You can't count on your library classes being co-evolved or co-compiled with its clients or its subclasses because they're in different maintenance domains. And the only contract you have, interface contract you have, is a binary one. You expect to be able to separately version libraries and clients. Not only do you take the opportunity to hide your internals from a maintainability perspective, but sometimes you actually have to do this to prevent users from attacking the integrity of the platform or subverting security constraints. So this all works really nicely, in a dynamically linked platform like Java. We're so used to this, we don't even notice, right? Assuming you've evolved your libraries in a reasonable way, you just drop a new jar on the class path and away you go, and nothing has to be recompiled. That's really cool. Well, object-oriented languages make this easy. They provide tools for precisely defining, navigating, and defending these boundaries. And so where OO really shines is in large code bases where programs span multiple boundaries, encapsulation boundaries, security, compilation, compatibility, and version boundaries. These boundaries help us manage complexity by limiting the scope of analysis required to a small region of code. if my clients were to tightly bind to my data representation, right? If they were just like to be able to reach into an object, grab my data representation out, then in order to verify a program is correct or to change my representation, I have to audit or change my entire code base. If representation is encapsulated, I only have to audit a small region of code. So obviously this is a big deal for security. It's also a big deal for correctness as algorithms get complicated. So like take an algorithm like concurrent hash map, right? Everybody who uses anything on the JVM is using concurrent hash map either directly or indirectly. Or the fork join pool scheduler, right? These are really, really tricky bits of code. And the representational invariants are really, really subtle, and even ignoring mutation, because I know some of you are thinking, if you didn't mutate, you wouldn't have this problem. The invariants are so subtle that you don't even know how to interpret the state. So it's a really good thing that the clients don't have to, in fact can't, try to reason about the meaning of the representation. They just work through the interface. So, you know, some people might respond, okay, I'm just writing an application, I'm not writing a library, so how does this help me, right? This just gets in my way. Well, the benefit here is more indirect, but it isn't any less real. As we evolve, you know, as we evolve the Java language, one of the things that we consider, one of the most important considerations we apply in considering any given language change is, will this change enable expressive new library idioms, right? You know, for me, the central point of language design is encouraging expressive libraries, because libraries have way more leverage than language. There's millions of people out there that can write libraries. Many fewer can write compilers. If you make it easy to develop and distribute great libraries, you get a rich library ecosystem, which means application developers have a variety of libraries that they can choose from and leverage. And not just application writers, language implementers too, right? Where would Scala be, you know, without, concurrent hash map, or, where would Akka be without the fork join pool, scheduler, right? That because you can just use these libraries as they are, you know, you can build you can build really useful things on top of it without having to worry about it. So this benefits everybody. It benefits the whole ecosystem. Okay, so speaking of boundaries, I highly recommend a talk by Gary Bernhard called, appropriately enough, Boundaries. In this talk, he outlines a style that he calls functional core imperative shell. And his argument is that within a closed domain, functional idioms, you know, are ideal. You know, you get great testability and composability, from value-based data and pure functions. And within the domain, we don't need those boundaries. We don't have a need for compilation boundaries or encapsulation boundaries or versioning boundaries, because all the code's maintained by one team. It's all compiled every time, you know, you run the thing. Those boundaries aren't serving you. But as you approach the parts of the system that have to deal with messy things like state and I/O and failure, the strengths of objects start to dominate. So this is a kind of diagram he describes it as, where little circles in the middle are functional entities, and the shell intermediates between the domain model and the messy real world and deals with the nastiness of state and I/O and failure. And the considerations of the boundary are completely different than those inside the capsule. Inside the capsule, you control all the code, it's recompiled together, it's maintained by the same people. But across boundaries, you have to think about copying and separate compilation and versioning and security checks and migration compatibility. So sometimes the shell is a class in our program that we wrote. Sometimes it's built into the runtime. So this diagram could describe an Erlang actor, right, where the shell is the Erlang runtime that deals with the nasty mutability of message queuing. And within the actor code, which is like all the code you see, everything is nice and clean and functional. All the messy stateful stuff has been pushed into the runtime. So it's easy to think of Erlang as being purely functional because you can't see the messy stateful imperative stuff, but it's there and it's imperative. So Erlang's actors are really a lot more like the classical objects I was talking about earlier. They're much more like K's objects than those we find in Java or C++. Microservices are really the same thing, right? Within the service, doesn't matter what's going on, functional idioms work really nicely. At the boundaries, they have to deal with I/O and state and failure, which is anything but functional, and they behave a lot like classical objects too. And so it's kind of amusing to me that in our desire to move past objects, and everybody seems to want to move past objects, we end up reinventing them over and over again, just giving them different names. So a small program could run like as a single instance of this shell, but as our programs grow, it might make more sense to represent it as a network of cooperating shells rather than a single monolithic one. And this again looks like every Erlang program ever written, right? And in designing systems, the really important architectural question is, where do we put those boundaries? Or to put it another way, what are my objects? And I don't mean like the low-level implementation classes, in Java or C#. I mean the classical OO objects, the independent entities that communicate with each other by sending messages. So this is another aspect of what I mean by rising above both object orientation and functional programming. We can use them at different granularities. We can use OO modeling to find the right places in our application to put boundaries and use functional techniques within the core. And one of the big complaints about OO is we have so many boundaries where they're not needed. But one of the things OO has to teach us, and has to teach the FP world, is sometimes boundaries in between you and yourself can be really helpful, can be really one of the best tools we have for containing complexity. So, while some members of the FP tribe like to tell themselves that FP is an evolutionary advance over OO, in kind of a funny way, the trend towards FP is also a step backwards along the same progression. So again, think of the conditions under which OO arose, right? In those days, the whole world was procedural. We had no language support for encapsulation or dynamic dispatch, although we could simulate them with discipline and function pointers, right? But inevitably, the same thing always happened. Clients would bind too tightly to our data representation, and this ultimately limited how much your program could scale. FP offers us much, much better tools for behavioral abstraction and reuse, but when it comes to data representation, it's a step back into the procedural world, where any client can access any data, which means everybody is tightly bound to everybody's representation, and that's going to limit the scale of our programs. So I want to get the best of both worlds, right? And we can get there once we let go of that toxic tribal worldview that says one must be strictly better or more powerful than the other. So FP models programs as transforms of their input, right? It excels when all you're doing is dealing with data. Inside the functional core, it's all just data, and that data all lives on the same side of all the boundaries. Similarly, because OO focuses on modeling active entities, it excels in system components that have to mediate between the program and the messier real world, such, like the imperative shell in Gary's example. And so the reason it's possible to rise above them both is that they offer complementary tools for managing different kinds of complexity, and we can apply a combination that might be more effective than either by itself. Another kind of more accidental and cultural way in which the trend towards FB is also a bit of a step backwards is how it acknowledges real-world complexity. So Brian Merrick is writing a nice little book called Functional Programming for the Outsider. And in it, he observes that in general, if you read what people write about functional programming languages, they tend to leave off the messy real-world problems outside of their documentation and examples. Whereas in a lot of writing about OO languages, they embrace the complexity of the real world, and they show, here's how OO can contain this kind of complexity. So if you read tutorials on object-oriented programming, you might actually come away with an understanding of how you might be able to apply it to like this crazy payroll system you're working on that's distorted by arbitrary tax law differences between 9 different jurisdictions and the weird union negotiation and compromise that was brokered 30 years ago. If you read tutorials on functional programming, they usually leave stuff like that as an exercise for the reader. So I think one of the dangers in falling in love with FP is it makes us want to believe we can make the real world as neat and tidy as mathematics. And FP is wonderful, but the real world is not as neat and tidy as mathematics. It just isn't. So we need to rise above the desire for things to be cleaner and simpler than they really are, and then engage the complexity head on with all the best tools that we have. And complexity is definitely the name of the game, right? We're awash in a sea of complexity, both inherent and accidental. And the central goal of programming language design should be providing us with good tools for managing complexity. And that there are so many languages out there, it illustrates that, well, A, we're not there yet, and B, complexity comes in a lot of different shapes and sizes, and no one tool is going to be perfect for containing it all. So it's almost inevitable that we're operating at the limits of our ability to manage complexity. When a better technology comes along and it allows us to build bigger systems without being overwhelmed by the complexity, what do? Well, first thing we do is we rebuild our world in the new image, right? Hoping that it's going to take us back to a lower complexity level. And then what do we do next? We make the system bigger, right? We keep making the system bigger and more powerful until, again, we hit the threshold at which we're barely able to contain the complexity. Martin, alluded to this in his keynote this morning, where he was talking about the cake pattern, where like people were early on very optimistic about the cake pattern and its expressiveness until we asked more and more of it, and then we ended up calling it the bakery of doom, right? That this is just how it works, right? And I don't think it can be any other way, right? The economic factors are always pushing us to building bigger and more powerful systems. So it's basically one trick that we have for managing complexity, and it has different names. You could call it divide and conquer, take a complex problem and split it into simpler problems and solve those. You could call it composition, which is the same thing, only bottom up, compose a solution to a big problem by solving small problems. Same thing, whatever you call it. And in our list of things that everything isn't, they all claim composition as their secret weapon. And it's not an accident, right? It's the only tool we've got. Functions compose, object compose, actors compose, right? No one paradigm owns composition, right? Any more than one paradigm owns garbage collection, right? So OO and FP are both guiding us towards this divide and conquer approach, just from different directions and at different granularities. So OO offers us encapsulation boundaries, which reduce global analyses down to local ones. FP encourages us to work with immutable values and pure functions so that behavior can be uniformly composed, from simpler building blocks into reliable, larger entities. What OO does for us works better with composition in the large. What FP offers us works better with composition in the small. OO's composition often gets in the way when you try to apply it in the small. FP's composition gets in the way because you inevitably end up binding too tightly to data representations, and that's going to put a limit on the scale of your program. So, this false dichotomy of FP versus imperative is often compared to a different false dichotomy, which is, should programming be more like math or like physics? And, as a mathematician, I love this comic. I'm sure you've all seen it. I love it because it feeds my sense of confirmation bias, right? I chose the right discipline to study in university. And I suspect a lot of functional programmers, feel the same way. But the reality is it's very easy to be seduced by the mathematics and lose sight of the fact that we are actually always running on a physical machine, and that actually matters most of the time. Pure FP kind of disavows any notion of resources like memory or threads or file channels, which means that resource management is the responsibility of the runtime. Now, often this is a good thing, right? Because that you as the programmer get to focus entirely on the business problem without being distracted by the bookkeeping. But sometimes it doesn't give us the resource efficiency we need to solve our problems in an economically feasible way. Imperative languages come at this from the other end of the spectrum. They start with the physics and work towards the math, and this gives us finer control, but at a cost, right? I think the whole focus on immutability is a little bit of a red herring, right? Immutability is great for some things, and it's not great for other things, and it doesn't exist in other domains, right? At the hardware, everything is mutable, right? So immutability is just an illusion that we pull on ourselves to try to help us reason about the problem. So it's great for modeling business data. It's considerably less great down at the data structure level. Most data structures are concerned with resource management. And functional languages don't offer us a lot of help with that. So almost all classical data structures use mutability because it allows much cheaper reuse than destroy and create does. And without mutability, we'd give up on cheap updatable hash tables, which is like the only trick we have for turning O of n problems into O of 1 problems. Don't get me wrong, purely functional data structures are really, really cool, but they're also a little bit of a dancing bear, right? It's impressive not because the bear dances so well, but that the bear dances at all. So thinking that programming is just math ignores the resource considerations. Thinking it's just physics ignores computational abstractions. So you could look at this, as glass half full, glass half empty. I like to look at it as glass half full, right? We get to play in this whole space over here, right? And we should be happy about that because we need both. And we should be comfortable in this whole space and not hide off to one side because the light is better over there. Okay, so I'm almost at the end, and you're probably still wondering, why did I call this talk, FP is dead, long live FP? And that is because I think FP languages, pure FP languages, are going to have a hard time competing with broad spectrum languages that let you choose where in the balance between these multiple paradigms you want to live. But that doesn't mean we have to stop doing functional programming. Far from it. It just means that we can't rely on the language to force us to do it. We have to make our own deliberate choices about how we want to program. Single paradigm languages force us to wedge everything into the paradigm, whether it fits or not. And the reality is most languages are built on top of something else, and sometimes you have to drop down into that something else to write your core libraries. You can't write Erlang's message dispatch in Erlang, you can't write the I/O monad in Haskell, you can't even write socket input stream in Java. And language implementers are always willing to throw themselves on that grenade for their users, right? Like our JVM guys like to say, we write in C++, so you don't have to. But when users feel like they have to drop down into the substrate language, that's usually not so good. And narrow spectrum languages give us a bad choice. Either split our program across multiple programming models with a terrible barrier in between them, or do without the things you can't do. In a successful broad spectrum language, you can write both your platform and your application without having to cross the barrier. And it's really a powerful thing that we can write high performance data structures like concurrent hash map in pure Java. This means, among other things, well, we're going to get more of those libraries, that's a good thing. Users with specialized needs can just go grab that code and customize it if they can understand it. And abstractions like Akka can just use it, right? And as time marches forward, languages that were traditionally object-oriented languages, like Java and C# are learning tricks from functional languages like, immutability and lambdas and coroutines and pattern matching. And despite the history, these techniques have nothing to do at all with functional programming. They're just good ideas that fit into a lot of different kinds of languages. Guy Steele recently did a keynote at JuliaCon called Lessons Learned from Fortress, which I recommend to everyone. And in it, he makes the point that it's the good ideas that we want to focus on, and they survive by hopping from language to language. And the language that develops the good idea may not be the one that popularizes it, right? It may very well be one of the worse is better languages. And, that's okay. So it doesn't really matter what language you're working in. Nobody can stop you from doing functional programming up here. And in fact, the best platform for functional programming probably is your brain. So, summing up, we all have so much to learn, and the problems we're trying to solve are so messy, we can't afford to ignore anything that we can learn from any programming paradigm. We can't afford to lock ourselves into a single paradigm just because we like it better. So we need to learn from functional programming, we need to learn from object orientation, and from procedural too, for that matter, and we need to rise above them all. So don't be a functional programmer, be a better programmer. Thank you.